Determine which graphs represent polynomial functions. Explain how you know. All right, let's try this. This one, polynomial function. How do I know? End behavior, negative infinity, and it just has that look to it. Up, down, polynomial function. Not a polynomial function, because polynomial functions go like this and have n behaviors that go off to either negative infinity or positive infinity. So it might go like this, or it might go like that, but they never have a horizontal asymptote. That won't happen because whatever the highest degree is, if you plug in a really, really, really large negative number, it's going to get really, really, really big, either positively or negatively. It's not going to go down to 0. If you plug in a large number, times itself, times itself, times itself, times itself, it's just going to get larger and larger and larger. It's not going to go towards 0. Definitely not a polynomial. Oh, I did a lot of writing. Let's get rid of some of that writing. No way. Yeah, gosh, not a polynomial. Polynomials have this shape, and they go on forever, and they go all the way up or all the way down. Maybe like this, something like that, where they go off to infinity, either upward or downward. This isn't even continuous. Polynomials are continuous. No. Yeah, this one looks like a polynomial. That's exact shape. This is actually a third degree polynomial. Right? So it's like y equals something x cubed plus something x squared plus something x plus something. Third degree. This one's fourth degree. Y equals something x to the 4 plus something x to the 3 plus something x to the 2. Yeah, this is totally a polynomial. This is degree 2. Y equals something x squared plus something x plus something. This is not a polynomial. Even though it kind of has the up, down, up, down, up, down, up, down look, it doesn't go off to infinity over here. It just keeps going up and down. This is like a sinusoidal, so not a polynomial. It's a little tricky, but not a polynomial because it doesn't have the end behavior that we know about. Determine whether each function is a polynomial or another type of function. Justify your decision. All right, I can handle that. This one is a polynomial. How do I know? We've got distinct terms. Each one has an x to the power of a whole number. X to the 3, x to the 2. This is actually x to the 0. So the minus 5 is minus 5x to the 0. That's allowed. This is a polynomial. Let's go to B. Yeah, polynomial. You got an x to the 2, an x to the 1, and an x to the 0, all whole numbers. The leading coefficients, or the coefficients of each one, doesn't even matter as long as it's some real number. Here, yep, this is a polynomial. Looks like they're all polynomials. This one's linear, so just degree 1. So you have 2x to the 1 minus 7x to the 0. Ooh, this one does not look like a polynomial at all, because this is y equals x plus 1 to the 1/2. Yeah, there are no rational exponents allowed. It has to be a whole number, so no, that's no good. Right here, no, that's no good either. This is like a negative exponent. This is like y equals x squared minus 4x plus 1. So far, so good. But then it's times x plus 2 to the negative 1. Not allowed a negative exponent. Right? So when you put it on the bottom, that's a way of faking that a negative exponent is a positive exponent. But we know better than that. Next, yeah, this one actually is a polynomial, this last one. Right? Because if I were to expand that, f of x equals, this is x times x minus 1 times x minus 1. Another way to put that is x. This is x squared minus x times x minus 1. Or I can say this is equal to x cubed minus 2x squared and plus x. So x cubed plus x. There we go. And yeah, this is a third degree polynomial. So yep, this one's good. All right, I'm going to erase all that writing and let's give a conclusion here. Oh, let's go. So yes, 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 no, no, and yes. This one's just in factored form, so it's kind of in disguise, but that is a polynomial. All right, finite differences we actually didn't have a chance to talk about today. We're going to talk about that tomorrow morning, but I might as well show you what it means. So it says here, use finite differences to determine the type of polynomial function that could model each relationship. If you remember a linear term, like a linear graph or a linear equation, has their first differences is the same. The quadratic, we learned their second differences are the same. And here, well, let's see what the differences are here. So if I take, so first of all, I have to make sure it's going up by the same amount. It's going from 0 to 500 to 1,000, 1,500. So it keeps going up by 500. Okay. And as it goes up by 500, what happens here? We get plus 25, plus 25, plus 25, plus 25. This is linear. Okay, which means degree 1. Okay, that's what y equals 25 over 500 x plus 200 is the starting point. This is the slope. So yeah, this is a line of degree 1 because the coefficients can be anything you want. You could have a rational, but this is x to the power of 1 and this is x to the power of 0. So yep, that is a linear polynomial function. All right, let's make sure this goes up by the same amount each time, and it does. So now I can take the differences. This is plus 15, oh, plus 5, oh, plus, oh, this one's minus 5, and this is minus 15. So the first differences, not the same. Let's go to the second differences. So this is first differences, second differences. Well, we're going minus 10, 15 to 5, minus 10. Oh, minus 10 again. This is looking promising. Yep, minus 10 again. This is looking like a second degree polynomial. So you're going to have y equals a x squared plus bx plus c. Or you can just say quadratic. All right, if it were cubic, then this would not be the same and this would not be the same, but then the third difference would be the same. If it was fourth degree, then that means the fourth difference would be the same, but not the first three, and so on and so forth. All right, draw a graph of a polynomial function that satisfies all of the following characteristics. All right, let's start it off. I'm going to draw my axes. We got my x, and I want to put y, but it looks like we're talking about f of x, f of x. All right, so f of negative 3, so let's put a negative 3 here. When x is negative 3, f of negative 3 is 16. So when x is negative 3, f of negative 3, which is y, so f of x, which is y, is 16. Let's go 16, put it right here, and we know that this is a point. But we also know that this is a polynomial function, which means it's going to look something like this, right? It's going to be smooth from left to right. When you get to the end, it's going to go down to negative infinity or go up to positive infinity, something of that nature. That's what polynomial functions do. F of 3 equals, oh, so over here, f of 3 equals 0. That's down here. So I know it's got to go through both of those points. F of negative 1.
Mr. Sean's here.
is equal to 0 as well. All right, it says the y-intercept is 2. Okay, I can do that. The y-intercept is at 2. So if that's 16, that's 8, 4, 2 down here. Okay, what else do we have? F of x is greater than 0. So the y value is greater than 0, which means it's above the x-axis, when x is less than 3. So that means from here, this is where x is 3, right here. From here this way, it has to be above, so it's got to be, it can't go below the ground on this side. All right? So that means from here to here, somehow I have to get it to go down. I can't go below, so it must touch and go back up. Like that. And on top of that, I know it can't go to negative infinity anymore because it can't go below the ground. So this can't happen. Let's go back. Let's give this a nice little curve this way. Come in like this. I may have to erase because I haven't looked at the other things yet, but so far so good. F of x is less than or equal to 0 says when x is greater than 3. So on this side, it has to be below or on the x-axis. So it's on this side, it has to be above. It can't be below, or it could touch, greater than or equal. And on the other side, it has to be below or equal. So it's not allowed to go above. The domain is the set of real numbers. Well, they didn't even have to tell me that. It's a polynomial function. Of course, the domain is a set of real numbers. That's how polynomials are. So now I could kind of do. It doesn't say what degree it is. Yeah, I could kind of do whatever I want on this side as long as I stay under the x-axis, and it's got to kind of have that look, that bumpy look all the way through, and it has to head off to negative infinity or positive infinity, but in this case it has to be negative infinity because positive infinity would cause it to go above the x-axis, and it clearly says f of x is less than or equal to 0 anytime that x is greater than 3. All right, state the degree, leading coefficient, and end behaviors of each polynomial function. All right, let's try that out. Here we have f of x is negative 4x to the 4 plus 3x squared minus 15x plus 5. Well, this is x to the 0. This is 5x to the 0, even though it doesn't show it. This is x to the 1, even though it doesn't show it. X squared, x to the 4. So the degree is whatever one's the highest, 4. Well, that should be easy. Degree is 4. Leading coefficient, well, that's the coefficient that's in front of the highest degree. So the leading coefficient is negative 4. End behaviors of each polynomial. Well, since the leading coefficient is negative, we know that as x approaches infinity, y approaches negative infinity. And since the degree is degree 4, so I'm going to just jot a little graph here. So I already said that it's a negative leading coefficient, so we know that it ends this way. And if the degree is 4, well, it just goes 1, 2, 3, 4. Okay, well, on the left, what's happening? It's going down. So we can say as x approaches negative infinity, which is on the left, y is also going down, so y approaches negative infinity as well. All right, let's do b. All right, b, the degree is, well, what's the highest one? So you got x to the 0, x to the 0, x to the 1, x to the 2, x to the 3, x to the 5 is the greatest. So the degree is simply 5. And next to that x to the 5 term is a 2. So your leading coefficient is 2. What else do we have here? Oh, the end behaviors. All right, so as x approaches infinity, well, the leading coefficient is positive 2, so y approaches infinity, right? Because if I make x really, 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 really big, positive, this x to the 5 is still going to be positive, and then you multiply by positive 2, it's still going to be positive. So it's going to be really, really big off to the right when x is really big. Okay, and what about the left? Well, the left is easy. It's a degree 5, so it's going to go 1, 2, 3, 4, 5. Oh, looks like we're starting very, very low. So as x approaches negative infinity, which is to the left, y is really, really far down, which is negative infinity. That's the end behaviors. Let's do C. Looks like they're trying to be a little tricky here. They're putting it out of order. This is an x to the 0, x to the 1, x to the 2, x to the 3. The highest one is 3, so the degree is 3. It doesn't matter what order they put it in. They're just trying to be a little tricky here. But normally in standard form, you would put this guy to the left, and you would do it, the proper way in standard form would be to go from highest to lowest. But that's okay. The degree is 3. Leading coefficient is the coefficient with that highest degree, so the leading coefficient, even though it's not actually leading right now because they mixed it all up, is negative 3. All right, since the leading coefficient is negative, we know that the end behavior is negative off to the right. So I can say as x approaches infinity, which means as x gets close to the right, y approaches, well, it goes down low, so negative infinity. And we said it is of degree 3, so we simply go up, down, up, 1, 2, 3. And so that means as x approaches let's try that again. As x approaches negative infinity, which is to the left, y is getting, so that it's going higher and higher, so y approaches positive infinity. And there we go. Let's do D down here. It's getting a bit crowded. D. H of x. Ooh, this one's a little tougher. All right, so since we don't care about any of the terms except for the leading coefficient, I'm going to start multiplying this together. But let's say 2x times x is 2x squared. And this is going to be 2x squared minus 10x, which really doesn't matter too much, times 3x plus 2 times 4x minus 3. So this is h of x. H of x equals, this is going to be 6x to the power of 3 plus something x squared plus something x plus something. I'm not doing all the math for that, so I'm just multiplying these two together. I just don't care what the rest are because that's going to be the highest degree anyways, and we only care about the first term. And so h of x here, when I multiply these two together, is going to be 24x to the power of 4 plus, I don't know, something x to the 3 plus, oh, I shouldn't use a, b, and c anymore. Well, I'm not. Just something x to the 3 plus something x squared plus something x plus something. All right, so this is going to be our degree 4 with a leading coefficient of 24. Now, if you want, you can expand this whole thing out and double check, but really it's just the highest degree of each one that's going to make any difference at all. So I know it's going to be 24x to the 4 something. But like, I mean, just this term right here is square, like a degree 2, this is degree 1, and this is degree 1. So I know when I multiply a degree 2 by a degree 1, I'm going to get degree 3. Multiply that by a degree 1, I'm going to get a degree 4. Try it out yourself. You guys know how to expand, right? Binomials. All right, I don't have much room here, so I'm making a little tiny graph here. And we're going to say it's a 4th degree polynomial, but the leading coefficient is positive, which means it goes off to the right up high. And it's degree 4, so it goes 1, 2, 3, 4, like that. So that means the left and the right are up high. So we can say as x approaches infinity, which is to the right, y gets really big. So y approaches infinity. As x approaches negative infinity, so way to the left, y still gets really big, goes really high, so it approaches infinity. All right, determine the minimum and maximum number of turning points for each function in question 1. All right, I already showed you the maximum. It could go up, down, so the maximum number of turning points, well, it's going up, and then it turns once to go down, and then it turns to go back up, and it turns to go back down again. So that's 3 turning points. 3 turning points. And the degree would have to be higher for it to turn any more than that. Like if we wanted it to turn again, it would have to be degree 5. So 3 turning points is the maximum number of turning points. But what these things could do, if the coefficients are just right, it could go up and then kind of, instead of going down, like down and then back up, that could all happen in like one spot. So it could just kind of like slow down and then go down, up like that. So it's kind of the same thing as going up, then down, then up, except this could be just like a little smaller, and then when you get to the extreme, it might just kind of fade off and not actually turn. So that is possible. And that takes away 2 turns, right? But then, so that goes 1, 2, 3. It still needs a 4th turn, and so that 4th turn is going to bring it back down again. Okay, so even though it should go 1, let's change the color so you can kind of see what I'm doing. 1, 2, 3, 4. Any pair of those, any down, up, can kind of fade away, and you could lose 2 of them. All right, so I could actually go down to, instead of 3 turning points, it could just be 1 turning point. But you can't do 2 turning points. If you have 2 turning points, 2 turning points would mean it goes down and then back up. It would lead upward, but that's not how 4th degree polynomials do. 4th degree polynomials have to end pointing the same direction in both ways. Okay, so you could take away pairs of turning points anytime you want. But I can't go any lower than 1 for 2 reasons. So if I could take away 2 more, but negative 1 turning points, that doesn't make any sense at all. Right, so that 1 is the lowest. But the other thing is, we know that it starts low and it ends low. Well, if it's going upward to start and it has to end downward, well, at some point it's got to turn at least once. It's impossible to not turn and then end going downward. Right, so you know there's at least 1 turning point. So anytime it starts and stops in the same direction, like if it's starting from high and ending high, well then you definitely had some turning point to get it back up there. So a minimum of 1. So the answer is the minimum number is 1 turning point, and the maximum number is 3 turning points. All right, part B, we already made degree 5. We know it could go 1, 2, 3, 4, 5. Well, how many turning points is that? So we're starting going up. You got 1 turning point to go down, 2 to go back up, 3 to go back down, and 4 to go back up. You should start to notice that the maximum number of turning points is just the degree minus 1. So the max is 4 here. But any two of them could kind of mingle together. So normally a fifth degree polynomial, I would say it goes 1, 2, 3, 4, 5, like that, with 4 turning points. 1, 2, 3, 4. That's normal. But it could put 2 together. So you can go, instead of 1, 2, 3, 4, 5, you go 1, 2, 3, 4, 5, like that. And now this kind of levels off, but it doesn't actually go from up to down. It doesn't go from increasing to decreasing, so it doesn't count as a turning point. This one changes from increasing to decreasing, and so does this one. And you'll see there are only 2 turning points. So you can have 4 turning points. You could also have 2 turning points, but you can't have 3. You can't just take 1 away. And I could actually do that instead. I could do that once. I could just do that again. So you're going up, you go down, up, down, up. Right? So it's like you're going up 1, 2, 3, 4, 5, degree 5. But it kind of has that shape of a degree 5, but it never actually turns down and then back up and down and then back up. So there's actually no turning points, 0 turning points. So but then of course you can't take away more turning points if there are 0. So the minimum is 0 and the maximum is 4. All right, part C, degree 3. You can see it goes down, up, down. Well, that's the maximum it can do, but it could do a double. So down, up, down means you have 1 turning point, 2 turning points is the most you can do. Remember, it's just whatever the degree is minus 1. So you could have number of turning points. You could have 2. But they could kind of mold together. So you can go, so a normal cubic goes 1, 2, 3. But you can put 2 together. So you go 1, 2, 3. And since this doesn't actually go back up and back down, it just kind of slows down, that's not considered a turning point. So it's going down the entire time, which means 0 turning points is the minimum. So your max is 2, your min is 0. You'll start to realize that an odd degree polynomial will have a max of whatever the polynomial is minus 1, which will be an even number, and a min of 0. It may not turn at all. So odd degree polynomials start from negative infinity and go to positive infinity, and they may just do a bunch of these fake turns, or they may actually go up, down, up, down, up, down. The number of turns would be the degree minus 1. Or they could go from positive infinity down to negative infinity in the same way. So they might not have to turn. Odd degree polynomials either start high and end low, or start low and end high. Whereas even degree polynomials will have an odd number of turning points. 1 less is the maximum. So let's say you have a degree 8. So you go 1, 2, 3, 4, 5, 6, 7, 8, if there are no tricky double turning. And the number of turning points is 7, right? 1, 2, 3, 4, 5, 6, 7 turning points. But they could pair up, and you can get rid of 2 at a time. So you can go 1, 2, 3, 4, 5, 6, 7, 8. Notice, even degree polynomials are going to start low and end low, or start high and end high. And the number of turning points will be an odd number if the degree is even. So the lowest you can go is 1 turning point, which makes sense. If you're starting high and ending high, well, there's somewhere it has to turn. If you start low and end low, it has to turn somewhere if you have a continuous curve. All right, what's my answer here? This is degree 3. So the max number of turning points is 2 with a min of 0. All right, let's see. This one, we have degree 4. And leading, oh, it doesn't matter the leading coefficient. We have degree 4. So it goes 1, 2, 3, 4. The max number of turning points is 1, 2, 3. Max of 3. And you know we could lose them in pairs. So it could go down to 1. It can't go less than 1. So your min is 1. Done. All right, the minimum and maximum number of zeros. So again, this is a polynomial of degree 4. The end behavior on the right is negative, so it goes like this. The most this thing could cross the 0, since it's degree 4, it could go 1, 2, 3, 4. So the most it could do is once, twice, 3 times, 4 times crossing this x-axis or touching this x-axis. So the max number of zeros is 4. Now what else can this thing do? It could go 1, 2, 3, 4. So it could actually have 2 zeros here. It could actually have 3 zeros if you're smart about this. You can go 1 and just touch 2, 3, 4. So this is like kind of like a double 0 here, but it just touches once. So that's 3 zeros. But you can do better than that. You can go lower than that. You can go 1, 2, 3, 4. You don't ever have to touch. You could have 0 zeros. Because it's an even degree, the whole thing could stay under the axis. It never actually has to cross and go up high. All right, so the min number of zeros is 0. You don't have to have any at all, like in this situation. So you could have 4, you could have 3, you could have 2, or you can have, oh, I could even do 1, actually. Let's do 1 for fun. So I can go up, touch, down, up, down. That's a 4th degree polynomial, up, down, with only 1 0. So you could go 4, 3, 2, 1, or none at all. All right, here we have a 5th degree polynomial. That sort of polynomial goes 1, 2, 3, 4, 5. So the maximum number of zeros, let's say it goes, this one has a leading coefficient that's positive, so it ends up. So 1, 2, 3, 4, 5. 1 0, 2 zeros, 3 zeros, 4 zeros, 5 zeros. So the max number of zeros is 5. Now I could go down to 4, 3, 2, 1, but the one thing I can't do is 0. So let me try that again. Let's go to 4. So I'm going to start high like it has to do because the leading coefficient is positive. And I'm going to go 1, 2, 3. I have to do 4, 5, but instead of going through the x-axis, I'm just going to touch it like that, 4, 5. So there's 1, 2, 3, 4 zeros. So instead of going through this and back through to get 2 zeros, I just touched it right there, so I kind of reduced it by 1 0. So this would be 4 zeros. Let's do it with 3 zeros. Well, I could go 1, 2, 3, 4, 5. I don't even have to go all the way up. That's 3. There are other ways I could have done it, right? I could have gone 1, 2, 3, 4, 5. I could have just touched this twice, and it goes through here. Okay, so these are examples of 3 zeros. Let's go to 2 zeros. You got 1, 2, 3, 4, 5. So that's a 5th degree polynomial. It's with only 2 zeros. Let's do 1 0. You're going to go up here. You go 1, 2, 3, 4, 5. That's a 5th degree polynomial with only 1 0. The one thing you can't do, though, is 0 zeros. Because I know it's an odd number of degrees, so that means it's high over here and it's low over here. Somehow you have to get from up here to down here. So at some point you go 1, 2, 3, 4. I have to go through. So the minimum number of zeros is 1. So an odd degree polynomial has to have at least 1 0 because we know the end behaviors are opposites of each other. Okay, now that we've investigated a lot, we can go a little quicker. This is a third degree polynomial. So let's try and let's see, the leading coefficient is negative. So that means it ends down low. So the most zeros would be 1, 2, 3, 1 0, 2 zeros, 3 zeros. So max of 3. The min, well, I know I could go 1, 2 without touching the zeros, and then I have to go up. So it goes 1, 2, 3. Now I'm going upward. Well, there's only one place to go without turning again. If I turned again, that would be a fourth degree polynomial. So I do have to go through at least once. Again, it's an odd degree polynomial. You have to go through once because you have to end low and start high, or end high and start low. All right, so part D, we already determined this is degree 1, degree 1, degree 1, degree 1. When you multiply them together, this is going to be degree 4. The leading coefficient is going to be 4 times 3 times 1 times 2, so 24, positive. Leading coefficient is positive 24. And so we know it ends up high. Fourth degree means 1, 2, 3, 4. That's for the maximum number of zeros. I make it cross the x-axis each time. So max of 4. And then you can reduce it one at a time by doing our little tricks. But let's try to make no zeros whatsoever. Can we do that with an even degree polynomial? Well, yeah, because we're starting up here. 1, 2, 3, 4. It never does have to hit the x-axis. So with an even degree polynomial, you can go all the way down to 0 zeros. No zeros at all. So minimum. And in general is, if you have an even degree polynomial, the minimum number of zeros is 0. You don't have to have any. If you have an odd degree polynomial, then you're going to need 1 minimum. And the max for any number, any degree, is just that degree. Yeah, it's just that degree. That's the number of zeros you can have. Every time it turns, it could go back up and hit x again. You know that. Like for a line is a polynomial of degree 1. We all know that it can only cross once. For a quadratic, we know that it can cross twice. Right? It could have 2 zeros, but can never have a third zero. Well, a cubic can have a third, a quartic can have a fourth, a quintic can have a fifth, 6th degree polynomial can have a 6th, and so on and so forth. All right, number 3, for each of the following graphs, decide if the function has an even or odd degree and the leading coefficient is positive or negative. So let's start if the function has an even or an odd degree. This one ends down and starts down, so that means even degree. This one ends down but starts up, odd degree. Ends down but starts up, odd degree. They both are down, even degree. They both are up, even degree. And one's down, the other one's up, odd degree. When they're both the same, it must be an even degree. And when they're both opposite, it must be an odd degree. Right? Because if you start low and you just go up, that's 1. 2 brings you back down. 3 brings you back up. 4 brings you back down. 5 brings you back up. So each odd number will pull you away from your original spot. Each even number will push you back to your original spot. All right, part B, the leading coefficient is positive or negative. Well, the leading coefficient dictates what happens off to the right. This one's going downward into the negative, so the leading coefficient is negative. This one's going down to the right, so negative. To the right, this one's going down, so negative. This one's going down, so negative. Oh, this one's going up, so this one has a positive leading coefficient. And this one's going up, so positive. That was easy. Describe the end behavior of each polynomial function using the degree and the leading coefficient. The end behavior or the end behaviors? Okay, well, I guess we're going to do end behaviors. All right, I think that's what it meant. So x squared. So first of all, the leading coefficient is positive, so it's going to end up. And since it's degree 2, it's 1, 2, it means it's going to be up and up. I'm just going to do the short form like that, and then I'll write it out in the long form for you guys in a second. So the leading coefficient here is negative, so that means it's going to end down. And the degree is odd, specifically 3, so 1, 2, 3. If it's odd, then they're going to be opposite, minus and plus. Leading coefficient here is 5, so it means it's going to end up. And since the degree is odd, it's going to be the opposite, so it's going to start down. So it's going to end in the positives and start in the negatives. Leading coefficient is negative, so that means when I plug in a really big number for x, it's going to be a negative. The answer is going to be negative. And since it's degree 4, both sides are going to be the same. So negative, negative. Over here, the leading coefficient is positive, so it's going to go up. And degree 4, that's even, so they're both going to be the same. So up and up. And last but not least, the leading coefficient is negative, so ends down. And odd degree, so it's going to be opposite. It's going to start up and end down. So this one is, all right, since it ends up and starts up, that means as x approaches infinity, y gets bigger, so positive infinity. Also, as x approaches negative infinity, y approaches infinity. It goes up on both sides. I'm not going to bother doing it for each one of them. If you guys have any questions with that, I can just help you individually. Use the end behaviors, turning points, and zeros to match each polynomial equation with the most likely graph below. Explain. All right, we have degree 3 and a leading coefficient of 2. So leading coefficient of 2 means it's ending upward. Degree 3 means it's probably going to go 1, 2, 3. So let's see which one does that. This goes 1, 2. This goes 1, 2, 3, 4, 5. This one goes 1, 2, 3. Yeah, this one looks pretty good. Let's call this one A. Well, let's just double check here. This one also does that 1, 2, 3. Maybe this will be A as well. This is a candidate. Let's check more stuff first. This one goes 1, 2, 3, 4, and 1, 2, 3, 4. They both end up. All right, so we're in end behaviors we checked out. Turning points, the number of turning points, and zeros. Oh, the zeros. All right, so a 0 means when does it equal 0? All right, so it's between these two. At this point, it's probably easiest just to say, what happens when x is 0? Well, it's going to be 2 times 0 times 0 times 0. So this is going to be 0, 0, 0. This is going to equal 2. Whereas this one, 0, 0, 0, this is just going to equal 1. So the y-intercept here is 2. The y-intercept here is 1. That means this is 2. Right here it's 1. So this is D. There you go. Let's do part B. We have a quartic, degree 4, with a leading coefficient that's negative. So leading coefficient that's negative means it's ending down. Degree 4, 1, 2, 3, 4, also starting down. So it can't be this, it can't be this, it can't be this. It has to start down and end down. Can't be that, can't be that. Oh, we got it. This one is A. All right, let's do part C. So this is a quadratic, degree 2, and the leading coefficient is just 1, so it's positive. So it ends up, and since it's quadratic, it goes 1, 2, so like that. Looks like it's that one. Definitely not that, not that. This one has the right end behavior, but look, it goes 1, 2, 3, 4. Too many turning points. And definitely not, so this is definitely not. So this must be E. D, let's go. We got 4th degree with a leading coefficient that is positive. So positive leading coefficient means it ends high. degree 4 means it goes 1, 2, 3, 4. So it's going to end high and begin high, and it's got 4th degree. So definitely not. It has to begin high and end high. So none of these are any good. These both end high and begin high, but it's 4th degree. So 1, 2, 3, 4. This is the one. So this is C. All right, here the highest degree is 5, and it's a negative leading coefficient. Negative leading coefficient means it's going to end downward. And 5, 1, 2, 3, 4, 5, it should begin upward. So up on the left and down on the right. No, this is up and up. Oh, here we go. Up on the left, down on the right. See if there are any others. No, 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 and no. So it's definitely going to be this one. But let's just double check that it's degree 5. 1, 2, 3, 4, 5. Yep. This is F. And lastly, it's leading coefficient, which is positive, so it's going upward. Degree 3, 1, 2, 3. Remember, it was one of those ones, but this one had a lower y-intercept, so that was this one. So this one is B. Number 6, give an example of a polynomial function that has each of the following behaviors. As x approaches negative infinity, so that's to the left, y approaches negative infinity. So to the left, it's going downward. As x approaches infinity, that's to the right, y approaches infinity, so it's going upward. So I know the leading coefficient must be positive, and it has to be an odd degree. So it does its thing and goes downward here. So let's just say y equals positive leading coefficient, because it ends up, so 15, and make sure it's x to the, let's say 7. That's an odd degree. Plus 3x minus 1. The rest doesn't matter. As long as the highest degree is a odd number, so that it ends and starts in 2 different ways, and the leading coefficient is positive, so that it ends on the plus side. Part B, as x approaches positive or negative infinity, so on both sides, y is infinity. So on both sides, it ends high, very high. Okay, so that means since it ends high on the right-hand side, the leading coefficient must be positive. So let's go 15 again. Why not? As long as it's positive. And the degree must be an even degree. So let's just say x to the 8 plus 3x minus 1. None of that matters. It's just the fact that it's even degree and positive. All right, part C. Let's get this stuff out of the way. Part C says, as x approaches plus and minus infinity, so both sides, y is negative infinity. So negative on this side, negative on this side. So since they're both the same, we know it's going to be even degree, but it's ending low, so it's going to be a negative coefficient. So let's say negative 15, x to the power of, it's got to be an even degree, let's do 4. And then plus 3 minus 3x maybe minus 2. None of that matters. You could go 3x squared, you could go 3x cubed, 2x squared plus x minus 4. It's just the highest degree that has to be even, and the leading coefficient for that has to be negative. Right, as x approaches negative infinity, y approaches infinity. So on the left-hand side, y is going up towards infinity. As x approaches infinity, which is on the right, y is negative. Okay, so since this is negative, we need a leading coefficient, which is negative. Y equals negative 10. And since they're different on the left, sorry, on the right and on the left, it's got to be an odd degree, so let's go 5. And then the rest doesn't matter. Plus 10x to the 4, plus 10x to the 3, plus 10x squared, plus 10x plus 5. These could be pluses or minuses. None of that matters. It's just the leading coefficient and the highest degree that matter. Sketch the graph of a polynomial function that satisfies each of the conditions. Let's go A. All right, degree 4, positive leading coefficient. So the positive leading coefficient has to end up high. 3 zeros and 3 turning points. So it's got to be degree 4. So you're going to go 1, 2, that's already 2 zeros, 3, 4, like that. Okay, so this 1 0, 2 zeros, and I just had to touch the x-axis because I didn't want a 4th 0. I'm only allowed 3 zeros. All right, and 3 turning points. Let's just double check. You went down, you turned once, you turned twice, and you turned 3 times. And it's degree 4 because we went 1, 2, 3, 4. There we go. All right, let's go B. We're saying degree 4 again, negative leading coefficient, so it's going to end downward. 2 zeros and 1 turning point. All right. So we're going to go, we're only allowed to turn once. So let's see how I can do this. Go like, okay, degree 4, so I'm going to go 1, 2, 3, 4. All right, so I've gone through here, I've gone through here. It looks like a 4th degree polynomial. It goes up, down, down. Now this down, up, I say down, up, but it doesn't actually go down again. It just kind of slows down as like the shape. Normally it would go down, up like that, but you can make that such a low hill that it actually doesn't go down. So it doesn't count as a turning point. It's constantly going up and then finally has a turning point right here. That's the only turning point. So we have 1 turning point, that's good. We have 2 zeros, that's good. And it is degree 4 because of this little jog that I did here that kind of took care of the shape to make it a 4th degree polynomial. And it has a negative leading coefficient because it ends downward. C. Degree 4, positive leading coefficient. So I already know it's going to go up like that. And since it's degree 4, it's going to start from over here as well because it's an even degree. 1 0. Well, if I go through, then I'm going to be forced to get another 0 in order to come back. So I can't do that. So I have to go just like this and just touch it and come back up. 3 turning points. So 1, 2, 3 turning points. So we got 1, 2, 3 turning points. 1 0. And degree 4, because it goes down, up, and a positive leading coefficient because it ends high. It's good. Part D. Degree 3, negative leading coefficient. So it goes like this, and since it's an odd degree, it's going to end up here. So it's got to go have at least 1 0, because it's got to go through somehow. Negative leading coefficient, done with that. 1 0. And no turning points. So it's got to go through, but it's degree 3, so it has to do this slow down and back up. I'm going to make that look a little nicer here. All right, so let's go up, down, up. Okay, I did a fake down, up here. We have, let's double check, no turning points, because this, even though it slowed down, I never actually went down. 1 0, that's good. Negative leading coefficient, that's there. Degree 3, it's all good. Let's go to E. All right, positive leading coefficient, so I know it's ending upward. Degree, an odd degree, so I know it's starting downward. It's got to start opposite from where it ends. 2 zeros, oh, so it's got to go 1. Ooh, it's got to touch 2, 3. It's not allowed to go through, otherwise it would have to get another 0. So 2 zeros and 2 turning points. Yep. So one turning point here, 1 turning point there. 1 0 here and 1 0 here. 2 zeros. We're all good. Part F. It doesn't say anything about the leading coefficient. That's nice. Degree 4, 2 zeros, 3 turning points. So 2 zeros. So let's go and arrange. Oh, so y belongs to R such that y is less than or equal to 5. So it's not allowed to go above 5. Well, if it can't go above 5, then it can't end high, can it? It has to be low. and low on both sides. And it's degree 4, so that agrees. 2 zeros, so it's got to go through, but 3 turning points. So it's got to get up to 5. 1, 2, 4, like that. So we got 2 zeros. We got 1, 2, 3 turning points. The range is anything less than or equal to 5. So I got up to 5, but didn't go past. And all the way down to negative infinity, so that's good. And it's degree 4. We got 1, 2, 3, 4. Yeah, we're all good. All right, so suppose we have f of x equals ax squared plus bx plus c. So that's a quadratic. What must be true about the coefficients if f is an even function? An even function means that if you plug, let's see, it goes like this, that the other side has to be exactly the same. It's mirrored on the y-axis. So if you plug in any x value, let's say you plug in x is 5 and you get that, well then negative 5 has to give you the same value no matter what. Well, for that to be possible, well, this x squared has no problem. So whatever I plug in for x here, a 5 or a negative 5, x squared will be the same for both. So this term, no matter what, it doesn't matter at all. It will be the same for both, because you'll get the same value whether you put in a positive or a negative. Same with this term. It's just c. It doesn't matter what x is. You're always going to get c as your answer. This is the only term that'll make any difference. Now, if I put in a positive number and a negative number, it has to always be the exact same thing. Well, the only way that could work is if, like, no matter what b is, if you multiply by a positive or a negative, it's going to be a different answer. So it won't be an even function unless b equals 0. If b equals 0, then it doesn't matter what x is. This is going to equal 0. All right, so what must be true about the coefficients? A can be anything, c can be anything, but b must equal 0. All right, part B is pretty much the same thing. We want this to be an odd function. That means for every, so it's a cubic, that means it has to be exactly the same on the right as the negative on the left. It has to have rotational symmetry. So it has to kind of go like this, and then it's got to be the exact same on the other side. Well, that's no problem here in the cubic part of it, because if I put in a positive number for x or a negative number for x, they're going to be equal to the exact same thing, except one will be positive and one will be negative, which is exactly what we want. So no matter what, this a doesn't matter at all. No matter what I put in for x that's positive, when I put the negative in, it's going to be equal to the exact same thing except the negative. Same thing with this. If I put like x is 9 or x is negative 9, well, c times 9 will be the same as c times negative 9 except the negative. No problem. The problem is with d. D is going to be the same no matter what, and we need it to be opposite. We need it to be negative or positive. Same with this one here. So an odd function, you can't have any even degrees in it. So basically you're talking about g of x equals ax cubed plus cx. This is going to be an odd function because it only has odd variables. So just like number 1, you have to have f of x equals ax squared plus c. Not allowed any odd degrees for it to be an even function. Here you're not allowed any even degrees to make it an odd function. So what can we say about a, b, c, and d, the coefficients? B has to equal 0 and d has to equal 0.